Hey, my dudes. We pick up with our discussion of mass defect. We saw that if you look at any nucleus, the mass of the nucleus itself is less than the mass of its individual parts. It seems strange. It is a little strange. The question is, how do you explain that? Well, sorry, I'm looking for my clicker. So we explain it using Einstein's theory of special relativity, or special general theory? Yeah, special theory of relativity that says that energy and mass are actually equivalent and can be related, oh boy, with the equation E equals mc squared. It's like the second to last video of the year, and we finally get to bring that out. All right? And so, the mass we look at here in this equation is our actual mass defect. And that mass defect accounts for something that we call the nuclear binding energy that holds the nucleus together. All right, we write this a little bit differently, and we say that the binding energy is the, remember, our delta M is our mass defect times c squared. Okay? There are, let's see, values of c squared. Well, the one thing you can do, let's see, how do I say this the best? Here's what I'm going to ask you to do. Am I going to ask you to do this or not? Yeah, I am going to ask you to do this. So, two things we need here. What I'm going to ask you to do, and this you'll bring in tomorrow, is this. I'd like you to calculate what we call the binding energy per nucleon of these two isotopes. Okay? And these two masses are called the bound, well, they are the bound mass. Well, no, I'm sorry, excuse me. They are the atomic mass. Both of these. All right? Now, so the binding energy, we already know how to do mass defect, right? If you want the binding energy, all you have to do is multiply by c squared, right? And then the per nucleon, right, that's just, we take the binding energy and divide by the number of nucleons. Fair enough? Okay, now, the one thing we need here is a conversion factor that's given to you in the AP reference table, and that's this, that one unified mass unit is equivalent to 931 point, well, not 0.5, they just use 931. Some things use 931.5. 931 MeV per c squared. So that means that you can write c squared as 931.5 MeV per u. Okay? I further challenge you to prove this. Prove to me that one unified mass unit is equal to 931 MeV per c squared. All right, that's just kind of a derivation with a bunch of different units. Okay? So, like, you have to be able to, you can use things like one proton is 1 point, I don't know, what is it, 7645 or something U. Well, we know that that's the mass of a proton. And we know what that is also in kilograms. So that actually starts to give you a thing between U's and kilograms. And, well, this is, right, a unit of energy. So somehow we can convert that to joules and, see if you can get that to work out. That's a challenge. You don't have to do that. This is your homework. Okay? That's it, folks. That is called a 5-minute video. All right? Here's how you do binding energy. Just calculate first the mass defect, multiply by c squared. We want binding energy per nucleon, divide by the number of nucleons. Okay? Enjoy, my friends. See you tomorrow.